Hello guys, you're welcome to this video on the applications of first order differential equations to heat conduction problems. So let's take a look at the question at hand. So we are told that the rate at which a body cools is proportional to the difference between the temperature of the body and that of the surrounding So if a body in air at 25 degrees Celsius will cool from 100 degrees Celsius to 75 degrees Celsius in 1 minute. Find its temperature at the end of 3 minutes. So the beauty about this kind of problems is that you get to formulate the differential equation yourselves based on the level of understanding of the question. And it's very straightforward. It's nothing difficult at all. So let's dive into this. Now, the first thing is we want to generate the mathematical model, that is the differential equation for this particular problem for us to be able to solve it. So let's set the temperature to be T. In degrees Celsius. So now we're told that the rate at which the body cools is proportional to the difference between the temperature of the body and that of the surrounding. Let the temperature of the surrounding be T, surrounding also in degrees Celsius. So now the rates at which the body cools can be written as the change in temperature with respect to time, and said it's proportional to the difference between the temperature of the body T and the temperature of the surrounding, which is T sur. So we can rewrite this now to be the T to be equal to K multiplied by T minus the surrounding temperature. And we're told that the body is in air at 25 degrees Celsius. So this means the surrounding is air and the temperature of the surrounding is 25 degrees Celsius. So we can write the temperature of the surrounding to be equal to 25 degrees Celsius. On substituting this, we have that the T now will be equal to K multiplied by T minus 25 degrees Celsius. Or you can just decide not to write the degree Celsius. Then you just leave it as dt to be equal to k minus k into bracket t minus 25, sorry. So we've completed the first and the most important step to solving this problem. So we have our differential equation as this. Oh, and I forgot to mention that k is a constant. So this is a first order differential equation, and you can solve this problem using separation of variables. So you can check out the videos on separation of variables in order to brush it up just in case you don't have an idea of it or you have forgotten it. So now we have dt divided by t minus 25 is equal to k dt. So you can integrate both sides from here. On integrating, we have the integral of dt divided by t minus 25 to be equal to integral of k dt, which can be written as k integral of dt. So in integrating this, we now have that ln t minus 25 is going to be equal to kt plus ln a, and a is an arbitrary constant. It has been written with natural logarithm just for simplification purposes. So we can combine ln t minus 25 and ln a. So we have that ln t minus 25 minus ln a is equal to kt. So using our laws of logarithm, we have that ln t minus 25 divided by a is equal to kt. So using laws of logarithm, we now know that t minus 25 divided by a will be equal to e raised to the power of kt, and t minus 25 on cross multiplication will be equal to a e raised to the power of kt. T now becomes a e raised to the power of kt plus 25, and we've successfully gotten the equation that describes the temperature of the body, general solution. We call this a general solution because we don't know the value of the constants a and k. So this solution now can call it equation asterisk. It gives the temperature of the body at any given time t. So now we need to find the constants a and k. We're told that at time t is equal to 0, the temperature of the body was 100 degrees Celsius. And also, at time t is equal to 1 minute, we know that t now became 75 degrees Celsius. So we can substitute these values into equation asterisk in order to obtain the values of our constants. So let's substitute t is equal to 0, that is the time is equal to 0 and the temperature got 100 degrees Celsius. We have that 100 is equal to ae raised to the power of 0 plus 25. We know that a raised to the power 0 is 1. So this becomes a plus 25. So we can collect like terms. 100 minus 25 will now be equal to a. That means a is equal to 75. So we can rewrite our general solution as t is equal to 75 e raised to the power of 80 plus 25. And all we are left with is to find k, or e raised to the power k, as the case may be. So t is equal to 75 e raised to the power of kt plus 25. Now substituting the temperature as 75 degrees Celsius and the time as 1, we have 75 is equal to 75 e raised to the power of k plus 25. We have 50 is equal to 75 e raised to the power of k. So we can divide both sides by 75. So we have that e raised to the power of k is equal to 50 divided by 75. So this becomes 2 divided by 3. So we don't necessarily have to find the value of k, because it's easier to just substitute 2 over 3 back into the original equation. So if e is equal to 2 over e raised power k is equal to 2 over 3, and we have that t is equal to 75 e raised to the power k raised to power t from our laws of indices plus 25, we have that t now becomes 75 multiplied by 2 over 3 raised to the power of t plus 25, which now becomes the general form, or the particular form in this case. Now we have the values of a and k, and we can easily solve for any other question. So the question now asks us to find the temperature of the body after 3 minutes, that is when the time is 3. So we can now solve that at t is equal to 3 minutes, we have the temperature to be equal to 75 multiplied by 2 over 3 raised to the power of 3 plus 25. So we have the t to be equal to 75 multiplied by 8 divided by 27 plus 25. So t now becomes 47.222 degrees Celsius. So this gives the temperature of the body at the end of 3 minutes. Thank you very much for watching this video. I hope you enjoyed it. See you in the next video.